This is a live recording of a lecture delivered under the title Equation of Motion. The agenda of this lecture includes points, distances, midpoints and linear interpolation, line and its parametric equation, equation of motion, speed, direction and velocity. So, points. This is a point. Things to consider when we think about points in terms of vector algebra, but also 3D graphics, is of course the coordinate system. You always have to remember that we have two different directions of the y-axis, screen resolution, location of the 0, point, which may be in different places, like here, but also here, okay? And also in the middle of the screen projection, translation, scale. So there is a lot of additional stuff to think about when you have a point. So points in 3D graphics are not so obvious. Okay, you always have to think about these additional things to consider. Clipping and windowing, so which part of the screen we can really see. The coordinate of the point in your game don't have to be the same as the absolute screen coordinates, and so on and so on. This only shows one very important thing, that whatever you do, you will most often need relational rather than absolute coordinates. The only moment when you really need absolute coordinates is the final drawing, okay? But all the previous calculations, and particularly physical calculations, will always operate on relative data. Point-to-point distance. And for this, we can apply the classical approach. Classical approach would operate on the coordinates. So x1 minus x0, x1 minus x0, that's the length of this edge of our triangle. This is of course squared and added to y1 minus y0, so that's the length of this edge here, squared, everything in the square root, done. Okay, that's the classical approach. This is not what we are trying to do right now in this topic of vector algebra, and in most other cases when you are doing professionally 3D graphics. Okay, so what we prefer much more is a vector approach. So we consider that this is a vector. This vector can be found as a displacement, and in calculating distance, because the distance from point A to point B is the same as the distance from point B to point A. So actually it doesn't matter if you subtract P1 minus P0 or P0 minus P1. It's important that you include this subtraction, okay? So you take these two coordinates of one point and another point, okay? You have to subtract these coordinates, and once you have it, you find the distance as the magnitude of your vector. Okay, so that's the vector approach. Now, if we know how to do the vector approach, we can do another funny thing, a midpoint between 2 points. Midpoint between 2 points is a point which is, first of all, on the same line as the points P0 and P1, and it's in equal distance from P0 and P1, okay? So, again, classical, absolutely classical approach, not a vector one, could be, well, let's take coordinates of P0 and coordinates of P1 and find the mean, or the arithmetical average. So it's x0 plus x1 divided by 2 and y0 plus y1 divided by 2. Okay, I hope you intuitively feel that this will give you the coordinates of the point between these 2 points. Okay, so x has to be between this and this, halfway through. So you add them together and find the half of the sum will give you the point in between. All right. Okay, so that's the midpoint between 2 points. But this is a very simple calculation in which, please note one thing, we do the same calculation on x's and the same calculations on y's, okay? Now think technically, if you do a similar calculation, let's say in a graphics card, okay? And this midpoint between 2 points, it's a trivial problem, but it may happen that you need to find the midpoint between 2 points in a shader. A shader is a program that you will learn how to write next year, not this year, next year. Okay, but shaders are programs executed by your graphics card. And these are programs that calculate, for example, the color of every individual pixel in your screen. Okay, so it is calculated thousands, sometimes million times per second, because it has to be calculated each frame for each point. It's basically in the shaders, in the shader programming, efficiency is everything. Okay. And now if you look at this diagram, formula, and if you think that this graphics card would have to calculate x coordinate of the midpoint and then y coordinate of the midpoint, and imagine shaders are usually 3D graphics, so there would be also the z coordinate of this point. It's terrible, okay? But if a computer can execute the same operation for multiple different data, it's something that can be done in parallel. So from the sequential architecture, we arrive to a parallel architecture of a computer, okay? And the parallel architecture of a computer based on multiple streams of data and the same way of processing them has even special name in parallel computer architecture theory, okay? And this name is a vector parallel computer, okay? And this is exactly what we do here. If I have the same formula for x, the same formula for y, this means one thing. I can change it into a vector formula. A vector formula will be faster on a proper hardware platform. It will be also simpler in your typical programming. I won't pretend that GFC will calculate this in parallel, but I will tell you one thing. This is something that GFC would understand. Of course, GFC would expect this thing like this. PM equals P0 plus P1. Sorry, I'm writing with my mouse. I know that's terrible. Divided by 2, semicolon. Okay, so this is C++ translation of this this formula that we have right here. Okay, this one. Sorry, not this one. This one. Okay, but it will work in GFC. All right, you don't have to look into the coordinates. If you create objects of the C vector class, and P0, P1, and PM would be the C vector class objects, then you can do such a calculation and you don't have to calculate all the x's, y's, and so on. Okay, next stage is this one. We take half of the vector P0 plus half of the vector P1. So, and if you add these two halves, you get the midpoint. It doesn't sound very intuitive, but it works. Having the midpoint, we can attempt to find a more general model for in-between points at different positions between the points P0 and P1. This problem is known in mathematics as linear interpolation between the 2 points. Basically, we have a parameter holding here a Greek letter name lambda, which describes the position of a point between the 2 ends. For the midpoint, lambda value is equal to 0.5 to reflect that this point lies exactly halfway through. So if lambda is equal to 0, then the linear interpolation value is here at the p0. For 1, it would be p1. And for the 0.5, it would be somewhere here at the midpoint that we have just done. So it's like a gradient, a parameter that will show us all the possible points between p0 and p1. And we start with 0 here, go through all possible values up to 1 here. At 0.5, we pass through the midpoint, okay? But this is the generalization of the idea of the midpoint between 2 points. Now we have not 50-50 like midpoint, but for example 20-80. To have a 20-80 proportion between the points, you would look for p with lambda equal to 0.2, okay? And this formula, it doesn't look perhaps very, intuitive, but this formula for a point in between p0 and p1 is like this. So you have to take 1 minus lambda times p0, add lambda p1. Lambda is a Greek letter, by the way. With values between 0 and 1, we can cover the entire segment from p0 to p1, everything in it. And in computer graphics, this thing is a very important function called mix or blend. Okay? Mix or blend. First of all, it can be used to draw a segment of line, okay? And we would say that to draw a segment of line, you have to take two ends of this segment and find all the blended values in between. But also, you probably remember that vectors can represent other things, like, for example, colors in the space of colors. And now, using this formula and iterating this lambda slowly from 0 to 1 across various values, you can create a gradient of colors. So a smooth transition between two different colors. This mix or blend function has many applications in computing. Now we have to go to another aspect of the same formula, because if you now think that this lambda could change from a negative infinity to positive infinity, so all possible values, this formula will cover entire line, so not just in between p0 and p1, but with negative values of lambda, it will be extension of this line from p0 to infinity and more. And with values greater than 1, it will go also to the infinity in the other direction. So yes, you can cover entire line. Now, what I propose is, a little bit of math. So 1 minus lambda p0 plus lambda p1, getting rid of this bracket p0 minus lambda p0 plus lambda p1, and extracting lambda from these two terms. Basically what I wanted to show you is that this form is the equivalent of this formula. So this formula is very nice because it is used as a mix, okay? But I will now introduce the vector p, and this is this red one. This is the displacement vector, so it's p1 minus p0. P1 minus P0 appeared in our formula here. Therefore, I will replace our formula. This is formula from which we started, and this is the equivalent formula. Okay, it's just mathematical, transformation of this formula, and we get something like this. This formula tells that P lambda, so any point on the line, can be given from the p0, and p0 is one point through which this line crosses, okay? Plus lambda times p, and p is a vector which shows the direction of the line. And this is what we call a parametrical equation of a line. Okay, so to have the parametric equation of a line, you need to find any point lying on this line and any vector that would show the direction of this line, and that's it. You take this point plus the vector multiplied by a parameter. Okay, so this lambda is just a parameter. Please note again, if lambda is equal 0, we are here at P0. If lambda is equal 1, we are here at P1. If lambda is anything between 0 and 1, we are somewhere in this segment here. And this is area of lambda beyond 1, more than 1. And here is the area of lambda less than 0. Okay? And this is equation of motion. So it's nearly the same thing. The only difference is that I changed the names of the variables. So instead of lambda, I have now t. T stands for time. Okay? And I gave the name for this red vector. And this name of the red vector is a v, that's the velocity vector. And now I have an equation of motion. So P0 is position of an object in the given moment of time. Okay, so in time t equals 0, it's located at P0. The velocity vector has the direction showing the direction of the movement. Okay, and the magnitude of this vector shows the speed, and the speed is measured in units, whatever unit it is. It can be meter, it can be kilometer, it can be light year, it can be some kind of a artificial unit in your display system. Okay, basically this is the number of units per second. Okay. In real life, you would quite often measure speeds in miles or kilometers per hour, but in physics we will rather attempt to measure it in the per second thing. Okay, so this t is basically time elapsed from the moment where you were here in seconds. So if you find the position at the time equal to 1, okay, for 1 you are here. And this is exactly what the velocity vector is supposed to show. So the velocity vector shows you the direction and the particular point somewhere in the space, which tells you where you are going to be 1 second from now. That's the velocity vector. Okay. If I am moving with the speed 5 meters per second, for example, when the velocity vector will show some kind of a direction, but the magnitude of this velocity vector will, of course, be 5. Okay, if it is 5 meters per second is my speed, then the magnitude of the vector is 5. Therefore, the end of this vector, the arrow of this vector, will be 5 meters from me. But wait a moment, if I'm moving 5 meters per second, in 1 second I will be 5 meters away. So the vector, the velocity vector, is exactly what you are going to travel in 1 second. Now, everything here is what you are going to travel beyond 1 second. Okay, but you can also look into negative numbers. Okay, so this is 0, this is now, and this is your past. These are your past positions. So you can use this formula and put any time here, like 5 seconds, into the future, and you will get your future position in 5 minutes. But you also can go back, okay, and find your position 10 seconds ago, like P for t equals -10. Of course, please remember that unless you have a system that can understand vectors, this vector formula can be broken down into coordinates, right? And if you are writing your in-class test, you may eventually need to break down these vectors into coordinates. If you're using GFC, you won't, okay? GFC understands vectors. And yeah, so your x will be x0 plus xvt, where x0 is your coordinate at the time 0, so your initial position, and xv is the v coordinate of your velocity vector. Now, if t is time, then of course this vx, vy, the red vector, is the velocity vector. Speed is the numerical value, and this is the magnitude of the velocity vector. And we can also talk about normalized direction vector, and this is the normalized velocity vector, which I already told you when we started our exercise. So that's the normalized direction vector. The vector n is called normalized direction vector. If its magnitude is equal to 1, you have the formulas here, and that finishes the lecture section of this today's session.